Now we will talk about superconductors. You may be wondering why to talk about superconductors now, because they are actually perfect diamagnets. So let's talk about how superconductivity manifests itself in electrical resistivity and magnetic susceptibility. So superconductors undergo a transition from a state of normal electrical resistivity to zero resistivity when they're cooled below a critical temperature Tc. As you can see here, at high temperatures in a normal metal, the resistivity is dominated by electron-phonon scattering events. So that's electrons scattering of vibrations in the lattice, and at low temperatures the resistivity saturates due to impurity scattering in the metal. But for superconductors, when the temperature is below a critical temperature Tc, the resistivity actually becomes zero. So that's the first thing we need to note about superconductors. Uh, for a temperature below Tc, the critical temperature, we have resistivity is equal to 0. Uh, 0 ohm meter in SI units if you wish. Okay, so it is 0, exactly 0. And the other important thing is also for T less than Tc in the superconducting state, superconductors are perfect diamagnets. That is to say, the susceptibility is equal to -1. So we have two important things to note here. One is rho is 0, and number two, the susceptibility is -1. Of course, these are all in SI units. And the other important thing is, even if we have infinite electrical conductivity, it maintains a finite current. So how does that work? We will find out. So even though for T less than Tc, electrical conductivity is infinite, it may superconductors maintain a finite current. So how does that work? So how does this work? Well, let's think about it for a moment. If we write Ohm's law, the current density is electrical conductivity times electric field. This is Ohm's law. Sigma is electrical conductivity. E is electric field. And J is our current density, which is current I divided by area A. So with sigma infinite, this has to be going to infinity for T less than Tc. Okay, but how can you get infinite J when you have a finite current I? So if I is finite, then the only way you can get an infinite J is cross-sectional area through which the current passes, A, must become 0. So if you have a finite number divided by 0, you will get infinite current density. Therefore, the conclusion is that electrical current in a superconductor is a surface current. So we said a few important things: zero resistivity, -1 susceptibility, perfect diamagnet, and also we have surface currents because the current that flows through the superconductor is finite. Now, how does this perfect diamagnet property work? So if you look at the material in the normal state, when you turn on a magnetic field, you will see a flux through the material. But when the material is cooled below Tc, so this is T less than Tc, this is T greater than Tc, and we see that the flux is expelled. So all the flux goes does not go through the material, it's expelled, and basically you can see what the effect of this would be. The flux inside must be 0 for T less than Tc. Now if I write my constitutive relations between B, M and H, B is equal to mu 0 M plus H, the magnetic induction should be 0. That means M should be equal to minus H, and therefore the susceptibility should be -1. This is SI. If I write this in CGS EMU units, B is equal to H plus 4 pi M. This must be 0. Then M must be equal to -1 over 4 pi H, or chi is equal to -1 over 4 pi in CGS. So once again you see that chi SI is equal to 4 pi chi CGS. So as we found out in our previous discussion. Now if I take this one step further, I find that also since I can write B is equal to mu 0 M plus H, and the permeability mu is now mu 0 1 plus chi, so I divide this by H and I get mu is equal to mu 0 1 plus chi, and so I find that relative permeability is 1 plus chi. So what is relative permeability for a superconductor? It is 1 minus 1, which is 0. So an important property of a superconductor is a superconductor is impermeable for T less than Tc. That is, no field lines can permeate the material, can go through the material. So examples of superconductors, we have the famous YbCO, yttrium, barium, copper oxide, known as YbCO, is a high Tc superconductor. The critical temperature is 90 Kelvin. It's the first superconductor with a known critical temperature above 77 Kelvin. That is the boiling point of nitrogen. Okay, so nitrogen boiling point. That's 77 Kelvin. So another important material to note here is verified record for ITC is mercury, barium, copper, calcium copper oxide, Tc about 133 Kelvin. So these materials, basically YbCO and mercury, barium, calcium, copper oxide, they are known as layered copper oxide superconductors. Now, these are of course complex materials to work with. For elemental superconductors, there are especially two that are really important. There is niobium with a Tc of 9.5 Kelvin, and there is lead with a Tc of 7.2 Kelvin, and these are important, again high Tc, because Tc is greater than 4.2 Kelvin, that is a boiling point of helium. So these are temperatures that can be easily achieved in the lab environment. Now, one other feature of the superconductors you can see here, there exists a critical external field that you can apply to a superconductor, above which the superconducting state is destroyed. It becomes a normal metal. And this is actually, I have to clarify that this is for a type 1 superconductor. We will talk about types of superconductors in the next video. So this is the type 1 superconductor. So we can note here that the field which destroys the superconducting state at a particular temperature which is less than Tc is called the critical field. We show it with Hc. Okay, and this Hc, as you can see, is temperature dependent. So this is Hc as a function of temperature. The maximum current a superconductor can carry is also determined by the field created due to the electrical current. When the generated field exceeds this critical field, superconductivity will be destroyed. So for example, so let's ask maximum current a superconductor can carry. So what is the maximum current a superconductor can carry? Okay, so suppose that we have a superconducting ring. Okay, so you can see here there's a superconducting ring. The flux lines are expelled from this ring below Tc. So it has an inner radius and outer radius like this, and this is the center. Now for T less than Tc, the ring will exclude all the flux from its center. Now if I pass current through it, let's say that I have a current passing through this ring, in the superconducting ring, I calculate the magnetic field at the center. H0 will be, as we have seen, I2 divided by the average radius. So since the current will be flowing on the surface, we can say that it's basically the average of the inner and outer radii. I divided by 2r bar will be in SI units, the magnetic field in the center. So when this is SI again, when this field reaches the critical field, then we have the maximum current that we can flow through it. So 2R bar. So this basically gives us a maximum current value, HC times 2R bar. So what determines the maximum current that passes through a superconductor is its critical field. So it's the self field created by the electrical current that exceeds the critical field. At that point, the superconductor will go through a phase change and become a normal metal. Okay, so we're talking about superconductors as examples of perfect diamagnets. Superconductors have a zero resistivity below a critical temperature, -1 susceptibility, perfect diamagnets below a critical temperature, and the current that flows through a superconductor is a surface current. The chi value is -1 over 4 pi if we use CGS units. When the external magnetic field is applied to a superconductor, the fact that it expels all of its flux, is called Meissner effect. So this is basically an important effect in superconductors, Meissner effect. And the fact that chi is equal to -1 also implies that the relative permeability is 0, which means the superconductors is impermeable for T less than Tc. Important superconductors to be aware of, YbCO and mercury, barium, calcium, copper oxide, layered copper oxide superconductors are high Tc superconductors. For them, the Tc value is above the nitrogen boiling point, which is economically very important since our atmosphere consists of mainly of nitrogen. It's very cheap. Elemental superconductors, a simple if you're looking for a simple material that is a superconductor, we have niobium and lead with TCs 9.5 Kelvin and 7.2 Kelvin, which is above the helium boiling point, which is also easily accessible in the lab environment. The maximum field that the superconducting state can oppose is the critical field, and it basically determines the maximum current that can flow through the superconductor, because the current will always create a magnetic field, and if the self field created by this current exceeds this critical field, the superconducting state will be destroyed.